Welcome back. Today, we're taking a massive leap right into part 2 of our series on turning environmental liabilities into sustainable resources. We're going to tackle something that's usually written off as a devastating environmental disaster: acid mine drainage. But what if we completely reframe this toxic runoff? Today, we're going to look at it not just as pollution, but as a literal liquid ore body.
So here is our toolkit for today's explainer. 1. The liquid ore body. 2. Mastering the vortex. 3. The triple tug of war. 4. Nature's manta ray masterclass. And finally, 5. Building the better brick.
Let's kick things off with Section 1, the liquid ore body.
Okay, let's dive into this. Now, in our previous deep dive, we explored the biological and reticular chemistry approaches to remediation. But, sometimes biology just needs a heavy-handed assist from the hard sciences to handle the sheer volume and extreme complexity of mine waste. Take acid mine drainage, or AMD, for example. We're talking about a highly acidic solution, usually sitting somewhere between a pH of 2 and 6, which happens when iron sulfide minerals get exposed to air, moisture, and microbes during mining. And yes, it absolutely degrades water quality. It coats streams in that thick, rust-colored sludge known as yellow boy. It's bad news. But if you look at it from a slightly different angle, it is also a massive, totally untapped liquid ore body just packed with dissolved iron, aluminum, manganese, copper, and zinc. So the idea here is that if we can just master the physics and chemistry to separate all of that out, we can simultaneously clean the water and harvest some incredibly useful raw materials.
So the crucial first step is figuring out how to actually pull those valuable metals out of the solution. To do that, we use a really elegant concept called pH-controlled selective precipitation. Honestly, you can just think of this as a chemical ladder. As we add a base, say magnesium oxide, to gently raise the pH of the water, different metals start to fall out of this toxic parfait as solid precipitates. And they do it like absolute clockwork. Iron drops out first at a pH of exactly 3.5. Then you step up the ladder to 4.0 and aluminum falls out. Keep going to 6.0 and copper drops. Finally, zinc precipitates at exactly 7.0. By carefully tuning that pH, we're creating distinct, solid layers right out of the dissolved liquid. It's amazing. But it does leave us with a new problem. Once we have all these solids just floating around in the water, how do we physically sort them all out?
That brings us to Section 2, mastering the vortex.
To physically sort those newly formed particles, we have to turn to the true mechanical heart of our operation, the vortex, or more specifically, an industrial device known as a hydrocyclone. Basically, a hydrocyclone takes a slurry, which is just our mix of liquid and solid particles, and pumps it at incredibly high speeds into a conical chamber. This creates a really powerful spinning vortex. The heavier, larger particles get flung outward by centrifugal force, and they spiral down the outer wall to exit through the bottom. Meanwhile, the lighter particles get caught in this inner vortex that actually spirals upward, exiting right out the top. It sorts the particles by size and density perfectly. And the craziest part? It does all of this with absolutely zero moving parts.
But as it turns out, vortex physics can get pretty sneaky. Have you ever stirred a cup of tea and noticed that the tea leaves don't fly outward to the edges like you'd expect, but instead they gather in the dead center of the cup right at the bottom? Well, this is famously known as the tea leaf paradox. James Thomson explained it way back in 1857, and Albert Einstein even used it in 1926 to explain how rivers erode their banks. The secret here is friction. The friction on the bottom of the cup actually slows the liquid down. That weakens the outward centrifugal force right at the base, which creates a secondary flow that sweeps down the outer walls and inward along the bottom, gently pushing all those particles straight into the center. And researchers at Tongji University recently proved that this exact same paradox applies even down at the nanoscale. By intentionally taking advantage of this secondary flow and its localized concentration effect, they successfully manipulated nanoparticles to aggregate incredibly fast. In fact, they achieved ultra-fast gelation of high-purity gold aerogels in just 20 minutes, literally by just stirring the solution. So it really shows us that container shape and fluid dynamics aren't just there for mixing things up, they are actually incredibly powerful design tools for building advanced materials.
Moving right along to Section 3, the triple tug of war.
Let's see how all this builds when we level up our physics a bit. By introducing a strong magnetic field into our hydrocyclone, we create an ultra-precise, three-way sorting machine known as a Magneto hydrodynamic hydrocyclone. It's a bit of a mouthful, but here's how it works. Gravity pulls the particles downward based on their mass. Centrifugal force pushes them outward based on their velocity and the radius of the spin. But the new addition, the magnetic pull, Well, that only affects particles with magnetic susceptibility, like our metallic precipitates. Non-magnetic particles, like your plain quartz, sand, or clay, they're completely unaffected by the magnet. So this triple tug of war allows us to cleanly and perfectly separate those valuable metallic particles from the non-magnetic background silt. Now you might be thinking to yourself, wait a minute, mine waste is a super thick, muddy sludge. Isn't that just going to immediately clog up a vortex? Well, this is where we get into what we call the sludge advantage. A lot of these mine sludges are actually non-Newtonian fluids, specifically shear thinning fluids. Unlike water, which always maintains a constant viscosity, these sludges actually become less viscous. They flow much more easily when they're put under physical stress. So the intense high shear rates generated by that spinning vortex actively break down the structure of the sludge itself. Essentially, the faster you spin it, the thinner and more watery the sludge becomes, which conveniently enough makes it even easier to perfectly separate the particles.
Which brings us to Section 4, Nature's Manta Ray Masterclass.
As we continue to refine our vortex filter, we can actually look directly to biomimicry for some serious inspiration. After all, nature has been perfecting microfiltration for millions of years. Just recently, in 2024, MIT researchers revealed exactly how mobula rays, like the iconic manta ray, filter microscopic food out of the ocean. Turns out, they don't just use their mouth plates like a giant spaghetti strainer. Instead, as water flows rapidly over those filter plates, the fluid actually swirls at the mouth of each groove, creating a tiny localized vortex. This vortex acts almost like a knot of hair in a comb. It effectively blocks particles that are even smaller than the physical gaps in the filter itself, just bouncing them down into the ray's throat without ever clogging the system. It is just an absolute masterclass in rational design.
But all of this really brings us to a crucial engineering question. Once our hydrocyclone, our secondary flows, the magnets, and those biomimetic vortices have perfectly sorted all these materials, how on earth do we actually extract them without stopping the fluid flow and completely ruining the vortex? I mean, do we use selective underflow ports or maybe magnetic sleeves that can be instantly switched on and off? It is a genuinely thrilling challenge, and it's one that's just waiting for the next generation of engineers to solve.
And that perfectly sets up our final act, Section 5, Building the Better Brick.
So we've used chemistry and physics to pull all these valuable metals and clean silica sand straight out of a toxic sludge. But what do we do with all those leftover clean materials? Well, we build a better brick. Just imagine taking that clean silica sand we just separated. We can look to really innovative concepts like Marcus Kayser's solar sinter. This is a device that uses a massive Fresnel lens to focus raw sunlight, literally melting ordinary desert sand right into solid glass without using a single drop of fuel. Now imagine taking that concept and pairing that 3D printed glass with those highly porous aerogels we learned about earlier from the tea leaf paradox. By filling a 3D printed glass structure with aerogel, you create a translucent glass brick that lets natural sunlight in while providing ultra-insulating thermal properties. We've taken all of these concepts and literally turned toxic trash into a sustainable treasure.
Now, just for some quick educational context on how these materials might actually be processed industrially on a mass scale, there's a technique out there called susceptor-assisted microwave heating. It essentially uses microwave energy to rapidly heat ceramics to just extreme temperatures with incredible efficiency. But, and I need to be very clear here, I must strictly warn you against trying anything like this. This involves highly volatile, extreme energy transfer and is entirely too dangerous for any kind of home experimentation. So please leave that part to the heavily shielded industrial labs, okay?
Ultimately, we've seen how pH ladders, hydrocyclones, magnetic fields, and even biomimicry can completely transform a toxic liability into the very building blocks of the future. The physics and chemistry of separation are right there, just waiting to be utilized. So the only question left for you is this: how will you tune these physical and chemical knobs to build the next generation of sustainable materials? Thank you so much for joining me on this explainer. Stay curious and keep exploring.